Thank you. Hi, good afternoon, everyone. Thank you very much, Dick, for the introduction, and to the Simons Institute for inviting me, as well as for this great semester program that I have really benefited from participating in. So I'll talk about finding low-rank matrices and other structured objects, and we'll start with some very simple problems. So actually, Dick just told me that the purpose of this talk is to get anybody who knows about this topic bored in the talk. So we will do that. A lot of it, for those of you who know about finding sparse vectors and low-rank matrices, it will be a high-level review maybe, and definitely boring. So, but there will be some interesting stuff hopefully towards the end. And we'll talk about some open problems in this area. Okay, so first, we will be looking at problems that go by the name of linear inverse problems, which means, for example, you want to find a signal x that lives in Rn, given linear measurements y, that is a matrix phi times x, and they are m of these, and that this is a linear system of linear equations, but it's underdetermined, so m is typically much, much less than n. And in a way, the y's are compressed measurements of the unknown object or signal x, and we would like to reconstruct or recover the object or estimate the object. And the key is the x signal here is often not arbitrary, but has some kind of a hidden structure, and various notions of low-dimensional structure that we will mention. And the question one wants to answer is how many measurements are needed, meaning how big should m be for any reasonably like polynomial time method of computation, reasonable computation lead us to the correct solution. And while we will most of the talk about this setup, the phenomenon that we will point out actually happens in a lot of other related problems that are not of the form of linear inverse problem. For example, denoising problems, variety of denoising and regression problems, and a bunch of other problems, some of which will show up later in the talk. Okay, so two key ingredients are present in solving these kinds of problems. One is the structure of the signal that we want to try and recover. And here is where the convex geometry associated to the structure and to computationally friendly methods to approach that structure show up. And also, second ingredient is randomness. And typically, this is in the measurements or the observations or the samples. And the two together have a nice interplay. There's a big surge of activity in research areas that revolve around this problem. First one is compressed sensing. From late 90s until now, there has been a lot of research going on in this area. It has impacted image and signal processing applications especially, but also many other applications. We will see some concrete applications soon. Also, the area of machine learning, or also what's known as a subset of statistics known as high-dimensional statistics, which includes problems like recommender systems, or regularized regression and M estimators, or lasso, if you are familiar with any of these, learning graphical models, and so on. And finally, another area that has been less studied, but I mean, less studied from this point of view, is the area of dynamical systems, the study of dynamical systems. And here, for example, finding low-order dynamical systems or identification of systems is relevant to this type of problem. So what do we mean by structure? We start by the simplest one, talking about vectors in Rn, which only have a few non-zero entries. So this is the vector. The colored ones are the non-zero entries. Everything else is zero. You can imagine this happens in an appropriate basis, could be coordinate basis or other basis. So that's one type of structure. Another type of structure is when we are dealing with data that is in the form of a matrix, let's say n by n matrix, and it has a low rank, meaning it can be factorized into the product of two matrices of size n times something much smaller than n, that is R, that's the rank of the matrix, and R times n. And this comes up in the recommendation problem, for example, and the dynamical systems problems. And there are others as well. For example, group sparse vectors, where you have groups of non-zero entries appearing in a vector, and also some of low rank and sparse objects. And this will come up later in the talk as well. So these are the types of structures we are interested in, and they're all somewhat capturing being low dimensional in an appropriate basis. one problem that we will definitely discuss in the talk is, and comes later, is when you have objects that have more than one such structure at the same time. These are called simultaneous structures. So, for example, one example is if you have an object, let's say a matrix, that is both sparse and low rank at the same time. And this arises in several application problems we will see soon. Or you can have a signal that is both sparse and piecewise constant, for example. Each of these, again, are individual structures that could be studied separately, but you have an object that has both. Another application is when you have tensors that have low Tucker rank, and Tucker rank is the rank of all the unfoldings. So when you unfold the tensor in all different ways and look at the rank of these unfolded matrices, that also is, can be viewed as several structures at the same time in one object. All right, so applications of this. The biggest application of compressed sensing, so many of you have seen it, is in magnetic resonance imaging in MRI. And this actually, there's a popular article written in Wired magazine in 2010 about it. It's quite interesting to read. So what happens in MRI is that you have signals that either in the space domain or in the frequency domain are very sparse or have a sparse representation. That's this is an angiogram, for example, where you can see that it's basically a contrast-based image that already in the space domain is very sparse, but when they also do contrast enhancement, it becomes even more sparse. And this one corresponds to brain image that is in the frequency domain, radial frequency, and there are not too many non-zeros along each of these radial directions. So compared to the ambient dimension of these signals, which is pixel by pixel, a large number of pixels, the complexity of them represented by the sparsity in a basis is actually quite small. And so the goal is that, and the impact of compressed sensing is that it has given systematic methods to do faster acquisition and high quality reconstruction in this MRI setting. And very interesting application area. Another example is dealing with low rank matrix example. This is also very, very typical. So recommendation system, you can view the database of all the users and all the movies as a big matrix, and the rankings that users give to movies as entries of that matrix. And typically some of these entries, a few of them are known, most of the others are not known, and you would like to guess and fill in the unknown ones. And this can come up in any recommender system, even in these other settings, recommending objects or books to users, etc. So I think many of you have seen this, hopefully. This was very popular because of the Netflix competition some years ago. But the key is that this is an example of a low rank matrix, and the reason the overall ratings matrix is low rank is that you can factorize it as something that is movie features and users features. So because only a few factors really affect each user's taste. And in practice also, you can see that it is low rank, some practical evidence for it as well. So the third example is in the one in control theory or system identification. So here you have a black box dynamical system, let's say linear dynamical system. You pick a signal, input signal to apply to your system, and you observe the outputs. And these are time series now. So this is a time series, that's a time series. And suppose you observe some kind of a noisy output. For example, you obtain upper and lower bounds on the output, or you obtain the output plus some wiggly noise, and you would like to reconstruct the dynamics, the unknown dynamics here. And the order of the system, which captures the complexity of a linear dynamical system, is actually the rank of an associated Hankel matrix. And so it actually is a rank minimization problem as well, or low rank reconstruction problem. And the randomness and noise could be in your inputs or also noise in the outputs. Usually you try to pick or randomize your input a little bit to tweak the system in different directions, so to speak. And finally, the another example is, first we talk about a problem called phase retrieval, which is a problem in optics, where you are measuring, so you have actually some X-ray source and a sample or an object that the X-ray is hitting, going through some mask and then hitting this image plane, and a diffraction pattern is formed. And what happens in phase retrieval is that from this diffraction pattern you can only measure intensities but not phase. This is called phaseless measurement. We will see the details later. And in this setup, what happens is you can view your measurements as linear in terms of a matrix that is a rank 1 outer product of the true signal you're trying to reconstruct. And so that's called the phase retrieval problem, and it was studied, for example, in this paper. You can see more about it there. As well as others, it has been a very popular problem recently. But I would like to also point out the sparse phase retrieval problem, which is less studied, which is you want to do the phase retrieval, but you also know that each of these vectors you're trying to reconstruct is also sparse. So you have two structures, both rank 1 and sparse. And this issue of being sparse and low rank, for example, also arises in sparse principal component analysis, in cluster detection, and in several other problems. We'll see some of them later. Okay, so the talk is organized around basically these examples. We'll first talk about sparse vectors. That's our example 1, that the MRI example. And then the example 2 and 3, the system ID problem and the recommendation problem, deal with low rank matrices. The third one is actually a simultaneous structure problem. We'll talk about what's known about it. And there are very interesting open questions by the time we get to simultaneous structures that we'll discuss. So first, sparse signal recovery. Okay, this is definitely the part that will bore many of you, but let's do it very quickly. So this is one view of it, but it's particularly simple view that one can do very quickly. All right, so this is my sparse vector that I'm making measurements of. This is my measurement matrix. I'm multiplying the matrix with the vector, and I'm getting this vector y. And in general, if this matrix, it's a big fat matrix, is not full rank, it's losing information. So one can't recover x given y, but keep in mind we are only interested in sparse vectors. What does that mean? Well, x only had a few non-zeros, so it means it's only selecting a few columns out of the big matrix. So we're not interested in recovering any vector, but only a sparse vector. So what if, so this problem is not that bad now because this matrix is now full rank, full column rank. And so what if the phi matrix was such that all m by k submatrices will full rank? Then it sounds like we should be in an easier situation. And that intuition is actually true. And here's how to formalize it. This is a property, it's actually historically the first property that, or one of the first properties studied for this problem, but there are many other properties as well that capture essentially the same idea. This one is called restricted isometry property, and it appeared in the Candice-Romberg-Tao paper in 2004. So it says, this is one way to express it. It says that if the map phi, or measurement map, is such that when it's acting on two different distinct k-sparse vectors, its distance is the ratio of the output distance over the input distance is close to 1, then we are in good shape. Why? Because if I take two different k-sparse vectors, these are each k-dimensional subspaces, x1 is one k-sparse signal and this is another one. If I take two different ones and it goes through this map, the output is far apart. So it can be told apart. So we are not losing information in that sense. Now, we can also see why we have, so this is close to 1, this gain. The ratio of the output of the map to the input is close to 1 within some factor delta 2k. And this is delta 2k because we are looking at each vector x is k-sparse, then x1 minus x2 is 2k sparse. Anyways, so what does it mean? It also means that the singular values of 2k columns, submatrices that have 2k columns of matrix phi have to be close to 1. So it's a property of the singular values. If that's the case, then recovery will be okay. And intuitively, it agrees with our intuition that, yeah, we are in a good situation. And so intuition is that the map preserves the geometry of sparse vectors or sparse signals. And more generally, there's a much better or more general property that captures the same idea, restricted strong convexity or restricted eigenvalue property. And there are other conditions, but the intuition is similar. And this one is easier to draw at a very, very basic level. Now the question is, okay, how do I pick a matrix phi that has this nice property, that satisfies this property? Well, if you give me a matrix, to check it, I have to enumerate all possible submatrices, so that's hard. It's exponential in the number of columns. However, so there is some interesting deep insight from 70s and Goskin and Cushion that a random matrix does have this property with high probability in the following sense. If I take a matrix whose entries are IID Gaussian or they are IID plus minus 1 Bernoulli, and there's a whole host of other distributions I can pick from, by the way, is related to Johnson-Lindner-Strauss lemma, so any Johnson-Lindner-Strauss matrix, and they also don't need to be IID, etc. From these families, if I sample a phi, then it satisfies the property that I desired with a probability that goes to 1 exponentially as m, which is the number of rows of the matrix grows. And the c is a constant that depends on that delta constant in the previous slide. And if this happens with high probability in m, if m is on the order of basically k times log of n over k, but the dominant is k log n. And this interesting thing is this number is much, much less than n. It's basically proportional to k and log of n. So it's much smaller than n. So we can basically do reconstruction with a minimal number of measurements. And actually, this is information theoretically tight. Now, so how do we do reconstruction? This tells you that it's possible to reconstruct with the right way. Let's try to guess what the right way would be. Well, first, reconstructing a signal given linear measurement means I have this subspace where my x can live in, right? And I want to pick one vector that I want it to be sparse. So maybe the first thing that comes to mind is let's take the minimum energy vector in that subspace. That is the minimum L2 norm, closest to the origin. But then even from this very simple picture, you see that's not going to be sparse. This is the sparse solution, but this one's not. And this is very typical. L2 norm solution is almost never sparse and well known. However, as you all well know, the thing that works, or the norm that does the right thing, is L1 norm. The unit norm, a unit norm ball of L1 norm is cross-polytope, that it looks like this. It has sharp corners. And in this figure, and actually with high probability most of the time, it actually hits the right sparse signal at one of its corners. So minimizing the L1 norm, which means you blow up this ball from origin until it hits this hyperplane and you get that point, that actually gives you the sparse signal. And so here is the result. Here's the formal result for this scenario, that it says that L1 minimization for random, for example, Gaussian, and the reversions for the other distributions that I mentioned, as long as basically you have the appropriate concentration of singular values, the reconstruction with L1 norm succeeds with high probability if m is on the order of k log n. And there are many other related results around the same time as well. Okay. Now, why does L1 norm work, and why do we use L1 norm? Essentially, what we are interested in were sparse vectors. So it could be this vector, for example, it has one entry non-zero, or this one, this one. And this is a discrete set. And we all know that this is a hard set to search over. It's intractable. However, searching over its convex hull, which is the L1 unit ball, is much better. And in fact, the insight about L1 reconstruction already existed from a long time ago. In fact, people were using it in the 60s and 70s, especially in geophysics, and then later in statistics. But the rigorous results go back to very late 90s and 2000s. One way to see what cases work and what cases don't work in the reconstruction is to look at this is the L1 norm ball, and this red region is the subspace, that is the where my measurements can live. And what happens is, the question is whether this subspace crosses into the ball or not. Because if it does not cross into the ball, the minimizer of L1 norm subject to being on the subspace is this point, which is the right signal. But if the signal was here and the subspace actually crossed into the ball, the minimizing L1 norm will give you this point, which is not the correct solution. So this is the case in which you cannot recover your signal. And this is a good case. So the result essentially means with high probability, the good case happens. And it means that most in random subspaces don't cross into the L1 ball with high probability. And this result can be extended to having noisy measurements, which basically means you put a cube around this hyperplane, and your x lives there, and you get a robust result, which basically says you're not too far from the true signal within this much error. So you can actually give robust versions of the recovery as well. All right, so hopefully that was a quick review of recovering sparse signals. But keep in mind the main idea was L1 norm and its main and role and this geometry. Now for low rank matrices. What's a low rank matrix? What's the meaning of rank? There are many meanings. One is that the rank of a matrix is dimension of the span of the rows. It's also the dimension of the span of the columns. It's the smallest number R such that I can factor the matrix into a product of two matrices where the middle size is R. And it's also the number of non-zero singular values. They're all definitions, equivalent definitions of rank. Linear inverse problem for recovering and reconstructing a low rank matrix is find a matrix that has rank R that satisfies some linear equations. We can represent it by a affine map on the matrix. So A is a linear map from let's say n by n matrices to Rm. And we can also stack it into a big matrix and stack all the entries of the matrix into a big vector. So we can just write it as a vector matrix product as well. All right, what is the geometry of this object? The set of low rank matrices. We saw the set of sparse vectors were on the coordinate axes. For a set of low rank matrices, it's much harder to visualize, but if you have a 2 by 2 matrix, it's not that hard. So here we take a 2 by 2 matrix and we draw in 3D. So the variables are x, y, z. It's a symmetric matrix, three variables. And we can draw the set of matrices that make this rank instead of 2 be 1. And you get the set of red points here and the red points here. So every point here corresponds to an x, y, z that gives you a rank 1 matrix. For example, this one corresponds to this matrix. That's rank 1. This one corresponds to this one. That is also rank 1. Okay? And, well, so this would go to infinity because you can always scale the matrix. These are normalized. So their Frobenius norm or L2 norm is set to 1. Okay, good. So now if I have linear equations on the object and I want it to hit at the right point, a point that is low rank, it means that I have a hyperplane that I would like it to hit at the boundary of this set. Can I do that by minimizing the convex hull of this set? And the answer is actually yes. So early on, actually in work with Stephen Boyd, we looked at the nuclear norm of a matrix and its relation to rank, and we heuristically proposed it as a way to minimize rank or get a low rank matrix. What is the nuclear norm? It's the sum of the singular values of the matrix. And so sigma I is the ith singular value. And it's essentially playing a very similar role to L1 norm for the vector, like sum of absolute values of entries. And minimizing this can be written as a semi-definite program. So therefore, there are efficient algorithms to solve it, efficient in the sense of polynomial time. But practical methods we'll discuss a little bit later. Well, so if you let X be a diagonal matrix, you get back your L1 norm. So this is generalizing the L1 situation. And you can view the nuclear norm as the L1 norm of the vector of singular values. And note that actually when we take this convex, and it's the convex hull of the rank 1, the unit normal is the convex hull of the rank 1 matrices that we drew before. And when we minimize the norm subject to being in this subspace, we hit at one of the corner points of the ball, which is a rank 1 matrix. So in that sense, it has a sharp corner. Note that the sharpness includes curvature, and that's fine. It's still sharp for our purposes, and we'll make that more precise later. About algorithms, so this is just an aside because in this talk we won't discuss algorithms of how do you actually solve this nuclear norm minimization problem to recover a matrix. We just said it's an STP, it's a semi-definite program. So many algorithms can be used to solve that STP, and there are some specific ones. Of course, you can use interior point methods and specialize it to the structure of your problem. Proximal gradient methods, a whole host of first order methods with different acronyms, and block coordinate descent, etc. So there are many choices. But there's also recent interest in trying to parameterize the low rank matrix as a product of two matrices with the appropriate size that upper bounds the rank, and then use non-convex optimization on that parameterized form. And this idea goes back to Boer and Monteiro, but it has gained a lot of recent interest. You can do either gradient descent on that factorized form, non-convex problem, or alternating minimization. So it's non-convex, so you have to work very hard to show anything works, but it does actually work in some settings. So for example, for recovering low-rank matrices in specific problems like matrix completion or several other interesting problems. Another interesting new direction is that one reason people actually use this factorization approach is that the size of this matrix is, which is a variable in the optimization problem, is n by n, is very large, whereas each of these guys are n by r, where r is usually very small. So it's the memory issue. You want your algorithm to save memory. And another alternative way to do that, instead of writing it in factorized way, in some problems, is to use a sketched convex formulation, or an algorithm that is based on conditional gradient descent on the dual problem, together with keeping a sketch of the matrix, so that you can reconstruct the solution from the solution of the dual, the primal from the dual. So this is another approach that is really convex optimization, but it has a memory footprint on the order of the non-convex factorization. So these are two interesting algorithmic directions for how to save computation and memory along these lines, but I won't discuss them any further in this talk. So why does nuclear norm work, and what's the sample complexity? What's the number of measurements you need? So going back to the original setup we had, where measurement is a random, let's say random Gaussian measurement, in our work with Ben and Pablo, we showed that you only need the order of n times r times log n, where this log n was just an artifact and it can actually be dropped. So the order of measurements needed is n times r. So size of the matrix times the rank, which interestingly is actually the degrees of freedom of a rank r matrix. So it's pretty good information theoretically as well. So even to just write down such a matrix, you need on the order of n times r entries, because the number of numbers here is 2nr, and if you do the counting, it's on that order. So that is good. Nuclear norm does work. Then one of our motivating applications was this problem of filling in the movie ratings and recommendation problem, and there's no Gaussian measurement here. But while the proofs are much more complicated, still, if you make some assumptions on the matrix and some assumptions on the randomness of the observed entries, things still work. So for a large class of X naughts, they do work, and this led to the result of Candace and Rick, and a lot of variations on it and simplifications of it that came later. Essentially says that nuclear norm minimization recovers incoherent matrices that have rank r from order of n times r times polylog in n, which is really nice. That's, again, the degrees of freedom of the matrix. And incoherence means basically that you're just avoiding matrices that cannot be reconstructed by looking at their entries. Things where entries are all in certain parts of the matrix and they're not spread out. But if the entries are spread out in an appropriate sense, then things are okay. So the geometric picture is a bit similar to what we had before. In all of these problems, we have nice sharp corners at the object of interest. The unit norm, ball of the norm that we are minimizing has a nice sharp corner at the point of interest. One more problem that is very interesting and again has similar flavor, even though the setup is different, is matrix decomposition or demixing. Here you are given a matrix C, and you are told it's a summation of a low rank, of a sparse matrix and a low rank matrix. But both are unknown, and you want to actually recover, for given C, the sparse part and the low rank part. There could also be a compressed measurement version of this in which you are given compressed measurements of the C and you still want to reconstruct the C. So for this problem, initially this was studied by Chandrasekaran et al. And the result is that, yeah, you can actually separate. The question is, when can we do this, solve this demixing problem? So you can do it under some nice condition, angle condition between certain subspaces that basically ensures that A and B are separable. There's no confusion between them. And the condition essentially means that the low rank part is not too sparse and the sparse part is not too low rank. Once that is satisfied, then it's possible to do the separation. And this is an interesting problem. It has many applications. So for example, one can be that the low rank part is capturing some low order relation between some variables, and the sparse part are some anomaly, so anomaly detection. Or graphical models with latent variables, for example, where the latent variable part is captured by this low rank part. And many other applications, and there's a whole host of other papers as well. And for example, this paper by Trop actually gives a view that is similar to the cone analysis that we will see later for this problem. So this problem, it looks different, but again, similar ideas and techniques apply. Under the right assumption, one can solve it and do the demixing. You can also have noisy version of it, you can have noise added, etc. And again, there are robust versions as well. So what's the most general among all of these things that we have seen? And this is a paper, again, by Venkat Chandrasekaran and Ben, Pablo, and Alan Wilski. And I like it a lot because it clarifies the picture of what you should do once you have certain structures. So they actually give you a recipe. You start by atoms. So you want to, your object of interest is a linear combination of only a few atoms. And you start from the atoms, normalize them, take their convex hull, and you get a normal with some technical assumption. You get a gauge function, but can correspond to a norm. And then suppose this blue set is the norm ball. And then the signal that you're trying to reconstruct, let's say it's this X, and the subspace it lives in, that subspace that is consistent with your measurements is the green one. And so X is the unique minimizer if the intersection of the cone of all the directions that point inward to the ball with the subspace is only going to be at the origin. Or with the null space of your measurement map is only at origin. So if this holds, then you can reconstruct X by minimizing the norm induced by this set. And this is very interesting and general result. It crucially relies on a lemma by Gordon, also known as the escape from the mesh lemma, that for inverse problems, as a result of this, the number of measurements, linear measurements one needs to reconstruct an object that has that is a combination of only a few of the vertices of this ball is on the order of, it has the number of measurements has to be related to the quantity called the Gaussian width of this cone, of this descent cone. So what is Gaussian width is for every cone is defined like that. So it's expected value of the largest inner product of everything in the set with a random Gaussian vector. And in some ways, it's measuring how wide your cone is at this point. And this generalizes this intuitive notion of sharpness we saw for the L1 ball and for the nuclear norm ball. So it's very nice. There's this nice geometric picture for everything that works. Now, I want to talk about a set of problems. So far, it seems like in this area, everything's solved, right? Everything works great, perfect. There are hard problems left, and I want to actually talk about even something that initially might seem very simple ends up not being simple. And this is the case where you have one object that you would like to reconstruct, but you know this object has several structures at the same time, called simultaneous structures. So we just mentioned one of the examples would be sparse phase retrieval. Here's the phase retrieval problem in a little bit more detail. So I would like to recover a signal x0 from linear measurements that are called phaseless measurements because they have an absolute value. So linear measurement, meaning there is a measurement vector AI transpose, you take the inner product with your signal x0, that's a linear measurement. But then there's an absolute value. You're given only the sign or the magnitude of a complex number if it's in the complex domain. And that's your measurement. And the question is, how many of these measurements, how big should M be for us to be able to find a way to reconstruct the x0 from these measurements? So far, this is the phase retrieval problem. And you can reformulate it by a trick that you guys many of you are very familiar with, which is lifting. You define a new matrix that is the outer product of your signal with itself, call it X. And now my measurements, these things, if I square both sides, this is the same as the inner product of AI transpose with x0 transpose. So I can write it like that. So now I have measurements that are linear in my variable X. Right? They're linear in X. However, X has to be constrained to be rank 1. So it's a low rank reconstruction problem so far. I'm looking for a matrix that's positive semi-definite, rank 1, and agrees with some linear measurements. So falls under what we discussed about nuclear norm. But we are interested in the case where the signal is also sparse or has a sparse representation in some basis. In that case, there's two things going on. Not only this matrix is rank 1, but its factors are sparse. So it's outer product of, let's say, k-sparse factors. It's rank 1 and sparse, and for example, block sparse. Okay, so that's the type of problem we're interested in, two structures at the same time. So let's look at that a little bit more formally. So object x0 has several structures at the same time. And these are, let's say, familiar structures. For each individual one, we already know a norm that works. So sparsity, well, I know, I do L1 minimization for that. Low rankness, well, I know, I'll do nuclear norm minimization. So individually well understood structures. Each of these structures come with a structure promoting norm. And now we have more than one structure, so it should help us. We should be reducing the degrees of freedom of the object we want to reconstruct. And a typical approach that's used in practice, in fact, I have seen this quite often, is if you want to induce several structures in your model, why not minimize an objective function that combines those individual norms subject to your measurements? So the question is, would this work? Now, this is written very generally. For example, this is a composition of a function h with these individual norms, where h is any function from R plus to R plus that is convex and is non-decreasing in each argument. This assumption is so that the composition remains convex in X. We want to get a convex optimization problem. And under the composition rule, this will still give me something convex. What are specific examples? What are specific ways to combine these norms? Well, you can take a linear combination with some coefficients lambda I, some tuning parameters lambda I. You can take the pointwise maximum with some tuning parameters. Both of these result in a specific h. And these are tuning parameters, alpha I or lambda I. Okay? All right, so we want to understand whether the solution of this optimization problem, or when, for how many measurements would the solution of this optimization problem be x0, because x0 is the structured object that I took the linear measurements from. Okay? Okay, if there are any questions, by the way, stop me, especially this part. Okay, so what am I doing here? I'm actually solving a multi-objective optimization problem. There are several objectives here, right, that are combined together with this function h. So it makes sense to look at the Pareto optimal front. So I have norm number 1 corresponding to structure number 1, norm number 2 corresponding to structure 2, and I will plot, so I will pick an m, number m, has number of measurements, and then I carry out these measurements on my signal x0, and then we look at the set of all achievable x's and take their norms, L1 and L2 norms, and basically shade the region of space that is above the curve that satisfies these constraints. So that gives you the Pareto optimal set, and the boundary of that set is the Pareto optimal curve. That shows that when you're moving, if you fix m, as you move along these, this curve, you're trading off these two norms with each other. Now, I've put x0 here. x0 does not live in this plane, but what I meant is that this particular point corresponds to the correct x0, the signal that I want to reconstruct. Now, we can see that this is just a cartoon, but the idea is if the number of measurements is too low, for example, I have m1 measurements, then the Pareto optimal curve I get is this one, which has really nothing to do with the signal I'm trying to find. So as I go along this curve, there is no hope of finding x0. But when the number of measurements m increases, I'll eventually get curves that actually do have x0 corresponding to a point on their boundary. So the point is, when things are failing, it's not really what combination of norms should I take. Any combination is going to fail. So it's not the tuning parameter lambda that's causing the problem. Neither is what kind of h function I picked. So in the case where things do work, I have enough measurements and x0, the true signal, corresponds to a point on the Pareto curve, then I can recover it by picking the lambda appropriately. So then lambda is the slope of this line. Or I can even do it by picking the pointwise maximum, which corresponds to, its level set corresponds to this square thing, which hits at the right point. So once things are recoverable, I can do it in multiple ways. But the problem is not being recoverable. Recovery failure. So when does recovery fail? Well, that's actually not hard to write down for this optimization problem. It's a convex problem. We can write down the optimality conditions for it. And one particular arrangement of the optimality condition gives us this inequality, that if this side of an inequality is bigger than this side, then x naught is not the minimizer of the optimization problem and recovery fails. So this is basically writing the optimality conditions and flipping it to get something that does not hold. And the reason we are doing this is that to obtain a condition that says you need at least a certain number of measurements for the problem to work. Now, what does the theorem say? What does this side say? Well, so this side, the left-hand side, is the minimum over all vectors in the subdifferential of f at x naught, the minimum of the inner product of the normalized vectors in the subdifferential and the normalized true signal. So these bars just mean normalization with L2 norm. So this is looking at the angles between my signal and the subdifferential of the function that I am minimizing. And this side is actually only depends on my measurement matrix A and on the signal x naught. So this side depends on the function I'm minimizing f, and this side depends on A, the measurement. So this notation, by the way, is the set of subgradients of the function f at x naught. One property that we crucially will use is that when you have a composition of a scalar of h with these norms, the subdifferential of this function, every element of the subdifferential can be written as a linear combination of individual subgradients. So you have a summation of some weight wi times gi, where gi is a subgradient of each of these. And in fact, that's where the bottleneck comes from. Let's look at this a little bit more. So the left-hand side of the inequality depends only on the function that we are minimizing, the cost, the penalization, and the signal. And this thing cannot be made very small because subgradients are actually aligned with the signal. So it's a set of subdifferential has some alignment with the true signal. So this inner product cannot be made very small. And just intuitively. And the right-hand side depends only on the measurement matrix A and the true signal. And if I look at this side and I try to upper bound it, all I need to do is to basically, for random matrices, just use a lot of results from random matrix theory that says L2 norm of a random matrix times a vector, or the sigma min of that vector of that random matrix are bounded, or how they concentrate, and so on. And for many random ensembles, including Gaussian, but also many more, this side actually scales as square root of m over n, where m is the number of measurements. So m by n is the size of this matrix A, and m is the number of measurements, and n is the ambient dimension of x. So I'm eliminating the proofs, but if you have any questions, I can show you later. Essentially, the idea is, what we do is that we lower bound very crudely this side by using geometry of the subdifferential, and we upper bound this side also crudely using concentration. Putting these two together, so we basically say this won't hold if this holds. So as long as m is less than some constant times n times this quantity, then the recovery program does not work. So this is a condition for the previous condition to hold. So recovery will not work. X naught is not the minimizer as long as the m is too small. So m has to be at least this quantity. Okay, what is this quantity? So the key thing is that this is actually, this kappa min is the minimum of the kappa I. Kappa I is a geometric quantity associated to each of the individual norms. And what it is that it's the ice norm of the signal we are trying to reconstruct divided by the Lipschitz constant of that norm. And what it's doing is that this quantity is measuring the ratio of the ice norm to L2 norm, or in the proper signal that we are trying to reconstruct. And the Lipschitz constant is the ratio of the change of the norm over L2 norm everywhere. And so this is basically how sharp your norm is, some measure of that. But the key thing is, among all of the individual norms, the minimum of them appears here. So you don't really get interactions between the norms. One of them dominates your bound. And to make it more concrete, let's look at some examples. So if I, for example, wanted to minimize L1 norm, so these are the familiar ones we showed before. If I minimize L1 norm to recover a k-sparse vector, my Lipschitz constant is going to be square root n. And the norm of the true signal, k-sparse signal, is L2 norm of it is square root k. So when I put them together here, m should be at least n times square of this thing divided by this thing, so you get actually k. So good, to recover a k-sparse vector, you need m to be at least k. And we know the true number is k log n. This is also true about column sparse matrices or group sparse, where you will be minimizing L12 norm. And here are the numbers, and the number of measurements you need is k times d. So in this case, my matrix is of size d by d, and k columns were non-zero. And now I have a rank R matrix that is d by d. The number of measurements with nuclear norm is going to be R times D, which is again the right number that we have seen before. So basically we reproduced everything we knew so far whenever we have a single structure. But let's look at the first example where we put together two structures. Here we have the nuclear norm and the L1 norm, combine them any way you want. The measurements needs to be at least minimum of k squared and R times D. But the true degrees of freedom of this object should be k times R. So this is the wrong scaling in the k. So this is where you see a gap. And actually, you can also show a gap in a little bit more detailed way for a problem that combines the nuclear norm and L12 norm for group sparse, but I will skip this. Because I want to point out one more thing. There is another problem that seems a little bit different, but runs into the exact same bottleneck. So the problem we talked about so far was a linear inverse problem. You were reconstructing an object given measurements, right? And we were asking for the minimal number of measurements for the reconstruction to work. And now this problem is a different problem. Statisticians are often interested in it. It's called denoising problem. So denoising means that there is a structured signal, x0, again in Rn. I have noisy observations of it. So I have x0 plus some noise, where noise is, let's say, Gaussian, zero mean, unit variance. So I add noise to it. And then I ask the question, how much noise can you tolerate and yet be able to exactly recover x0? Or not exactly, recover x0 in the way that scales the right way with the noise, with the variance of the noise. So one way to do it is this regularize least squares denoiser. It's a very common approach. So you build an estimator for the x given the measurements y that minimizes the distance between y and x, and it also penalizes or regularizes using an appropriate norm that took the structure of the unknown object into account. So for example, if it's a sparse vector you want to reconstruct, you will plug in L1 norm here, or nuclear norm. And so, by the way, this is a minimizer of this simple problem is nothing but a proximal operator, also known as the prox operator of the norm of lambda times the norm at y. So this proximal denoiser is very common, and nice things have been understood about it for single structure case. Now, in statistics, in at least a subset of literature that deal with this problem, the error of an estimator is measured as this mean square error risk, which is defined as follows. It's the worst case error that you can have in your reconstruction. So this is the reconstructed signal as a function of the noisy measurements, minus the true signal. This is the largest possible error over the signal to noise ratios. Gamma is the SNR signal to noise ratio. So among all signal to noise ratios, take the worst case, and that is the error. So that's the worst case error. And you want to then, you call that as your MSE as a function of lambda. Lambda is a parameter in the problem. Now, you can optimize over your parameter as well. So minimize over all lambdas this error. So that's in some sense a minimax mean square error risk. So over all tunings lambda, this is the best one. Okay? So what happens if you plug in the simple known structures? So for an x in Rn, that's a k-sparse vector, denoising with L1 norm, gives you an MSE error that scales on the order of k log n, which is good. It's again the degrees of freedom of the x0 object, k-sparse vector. And if it's a rank R matrix, again, this error, denoising with the nuclear norm, gives you MSE that scales with n times R. Again, the right information theoretic one. And these are results from various papers, Donoho and Ontonari and others. But what happens if you have multiple structures? If you have a lower bound, we can give a lower bound on the MSE risk for the case of multiple structures. And I won't give any of the proof, but actually one simple geometric thing is that what you can do is that the error is never better than the quantity that is determined by the largest angle between any of the individual subdifferentials and your signal. So among all the subdifferentials, this is for norm 1, this is for norm 2, pick the vector that has the largest angle with the true signal you were trying to reconstruct, and that dominates your mean squares error. So that means, again, the structures are not helping reduce the total error. It's dominated by only the one of these individual structures. So the one with largest theta dominates. And this is a simple way to see that, again, you have the same bottleneck as before, that combining the structures. So this is, by the way, I took the linear combination of the structures like that. But it's also true if you take, again, composed with a function h that is convex and monotonic in its variables. And also, the same result extends to the case where you don't just do denoising, but you're doing a regression. So you have the measurement map in here, and you have noise, and you're using the regularizer to reconstruct. So this is a typical estimation problem in statistics. Again, with multiple structures, combining regularizers hits the same issue. Okay, so this brings us to, I think, what's the most interesting part in the talk, which is this problem is still open. What does one do when you have multiple structures in one object? So we showed a very general negative result. A whole bunch of things don't work, right? But what can work? So likely there will be a case-by-case solution for each type of structure, but one of the most popular combination of structures is low rank and sparse. So matrix that is jointly low rank and sparse. And by the way, I want to point out that this relaxing the low rankness and sparseness individually using L1 norm and nuclear norm also appears in many typical STP relaxations where implicitly being low rank is relaxed to being in the PST cone as a constraint, and then there is some like trace that is being minimized. That's basically equivalent to nuclear norm for symmetric and PST matrices. So whenever you have X positive semi-definite and a trace in the objective, and at the same time you want some kind of an entry-wise structure and you use L1 norm or summation or equality constraints on the entries, usually this means you are handling your entry-wise part of the structure and the spectral part of the structure separately. And perhaps this is why a lot of these STP relaxations have limitations. So very, very vague. But so what can one do? In each case, one can first try to find a better penalty. Maybe the combination of the individual norms isn't the best thing. So one thing is going back to that atomic norm framework and see if one can identify the right atoms, take their convex hull, and see if one can get anything. That's definitely possible if it can be done. However, for example, for sparse and low rank case, it's actually interactable to do. Then people have proposed different sort of heuristically built approximations to try to improve. And there have been some improvements, but not order-wise. You're still stuck in the same order. But constants have been improved for specific problems of combining low rank and sparse. And then this one was for unfolding of tensors, the low Tucker rank tensor. And also another line of work has looked at the measurements. If you have the ability or freedom to construct the measurement map in a very specific way, you can get around this problem, but usually that's not available. So for example, if you can do nested measurements, you first make measurements that respect the sparsity, and then on top of that, make measurements that respect the low rank and so on. So that's possible, but only very restricted applications would allow such a thing. Now, one interesting thing is that I have been thinking about since the recent workshop in this program about SOS hierarchies. And the very recent paper that actually a lot of people here have worked on, I guess Hopkins, Stewart, Salil, and others, actually shows on the problem of sparse PCA, which is an example of a problem that has low rank and sparse structures together, that there are exponential lower bounds on SOS algorithms. And so it kind of hints this is a very hard problem. But it would be interesting to see if this machinery can be also used for other combinations of structures, either give positive or negative results, whether gaps can be bridged or they cannot be with binomial time algorithms. So I think that's a very interesting open question. And with that, I would like to just thank everyone, first the collaborators and also Simons Institute for this amazing program. And thank you all for listening.